Okay, so I think we should get started. So
Okay.
if you're okay, so let's get started.
Okay. So welcome everyone. So this will be the last lecture. Um, yeah, has the recording started, I guess?
Yes, start.
Okay. Okay. So today we're going to talk about we're going to sketch the proof of the paraboloid uh, in R3. Um, this will be based on Borgan and Demeter's. So there's a paper by Borgan and Demeter called A Study Guide for Decoupling for the Paraboloid. Or a study guide for L2D coupling or something like that. This proof will be based off that. I also sort of used Larry's Math 118 notes as a source. So if you want to look for sources, those are the two sources I use. But today, the overarching idea will be I will show you what is decoupling for the paraboloid, and then I'll sort of show you how do you reduce to the multilinear problem. And once you reduce to the multilinear problem, how do you analyze the multilinear problem? And then, of course, there's some iteration, but then the iteration itself will, well, I'll just skip because this is somewhat standard. Okay, so uh, let's see. Okay, so let's define decoupling for the paraboloid. So for Q will be a square inside the unit cube. Okay. So the picture will be, here's the unit cube. Unit here Q lives here, and then there'll be a little paraboloid that lives above it. Let's draw using a different color. Okay. So if Q is down here, of course it lifts to a certain cap on the paraboloid. Okay. So for Q in there, let theta Q. Let's see. This is probably slightly more readable. Theta Q be the delta squared neighborhood of the piece of paraboloid that lives above Q. Oops. Okay. So pictorially, um, it so if Q is of length delta, then pictorially theta Q looks like this. Okay. This is delta, and then this is a delta squared neighborhood. Okay. And then we're going to let d of delta be the best constant such that the L4 norm. So it turns out that the critical exponent to proof in in R3 is the L4. In general, the critical exponent in RD is 2 times d plus 1 over d minus 1. So when d equals 2, this is 6. When d is 3, this is 4. And you, of course, can give a similar discussion that we did in the parabola case, but we'll skip that for time. But d of delta is the best constant such that this is true. For all F Fourier supported in the delta squared neighborhood of the piece of parabola above the unit box. Okay, and there's some notation here. Some notation. So for S inside the unit ball, I'm going to let F S hat be defined to be F hat times the indicator function of S cross R. Okay, and so FQ is just the same as F theta Q. But it turns out that this is slightly more convenient to write. Okay, so this is just F very restricted to the piece of paraboloid that lives above S. Okay, so the main theorem of Borgan and Demeter, 2014, is that d of delta bounded by delta to the minus epsilon. Okay. So, What's an exercise? So let's give an exercise. Exercise. Show that to have the L4 norm bounded by delta to the minus epsilon. Okay, for all f Fourier supported inside this the piece of parabola that lives above the unit square. Oops. Qn. Okay. It is one needs sorry, this should be P. One needs 2 less than P less than 4. Okay. So this is the analog of that exercise where, so hint, one wave packet in each direction. Sort of the Bush example of one wave packet in each direction will show that in order to have this estimate, you must have P between 2 and 4. Okay, so sort of 4 is the right estimate. 4 turns out to be the critical estimate. Okay, so are there any questions at the moment for this setup? And I can see the chat, so if there are any questions, feel free to also type in the chat.
Thank you.
Okay. Okay, so implicitly, if I forget to assume, so for the rest of this talk, we will implicitly assume that f is Fourier supported in the piece of parabola that lives above the unit cube. Okay. If I forget to say it, usually I'll remember to say this, but if we forget, we're going to always assume that f is Fourier supported in a thin neighborhood of the paraboloid above the unit box. Of course, you may ask, why am I doing this unit box rather than 0, 1 squared? It doesn't make a difference. It's just more convenient to draw in this case. Okay, so there are some tools. Okay, there are some tools. Well, okay, let's go back so then, we can look at this. So tools. So the first tool that we'll make a lot of use of is the uncertainty principle. Okay, so what is the uncertainty principle stated here? And I won't prove it in the sense of show that it's the same heuristic reasoning that we talked about in the parabola case. It's just one higher dimension. So it's the same reasoning. So I'll state it so that you know what it is, and then we're going to use it as fact. So let G be Fourier supported in a 1 over r squared neighborhood of the paraboloid above Q, where Q is a unit in my unit ball, and the side length of Q is equal to 1 over r. So what's the picture? Actually, let's just copy it to the next page. Oops. Okay, so what's the picture? Okay, so the picture is, okay, so we have some Q down here, and it lifts to a certain neighborhood of the paraboloid. Okay, so it's 1 over r by 1 over r by 1 over r squared. The support of G hat lives here. Okay, so then what's the uncertainty principle? Okay, so the uncertainty principle says that then the absolute G is essentially constant. So by essentially constant, I'm just going to write constant in quotes. Essentially constant on any. Okay, so how do you remember the numerology? How do you remember the heuristic? You just sort of invert these sizes on any r by r squared tube. So what's an r by r squared object? R by r squared object is a tube. This is r by r squared tube pointing in the normal direction NQ. So what's NQ? NQ is so this is Q. Q lives down here. It lives down here in 0, 1, and it gets lifted. It gets lifted onto the paraboloid, and then that gives a direction. This piece of the paraboloid has a normal direction, NQ. And so then what I do is then I draw an r by r by r squared tube pointing in this direction. This is an r by r by r squared tube pointing in this direction. So then the uncertainty principle says then the absolute value of g is constant on any r by r squared r by r squared tube pointing in this sort of normal direction. Okay. Furthermore, and we're going to use this a lot today. Furthermore, absolute g is constant, essentially in particular, absolute g is essentially constant on any r ball of radius r, because you take any ball of radius r, right? You take any ball of radius r, here's a ball of radius r, or balls and boxes are the same. What I can do is I can fit it inside any translate. That's an r by r squared tube pointing in this normal direction. And since absolute g is constant on this whole thing, then absolute g is constant on the green box. Okay. Okay, so that's the uncertainty principle. The proof of why this is true is the same proof as in the parabola case. It's just more variables. Okay. Okay. So this plays a key role. So tool 1. What's the second tool? Okay, the second tool is we once again have parabolic rescaling. And I'll just state it. We won't use it so much today because we're going to concentrate on the other tools, which are new. But certainly it shows up in the iteration. So let's say if q tilde is a square of side length sigma, which is bigger than delta, right? How much does it cost to decouple the piece of paraboloid that lives above q sigma in L4? Well, it costs d of delta over sigma. How much does it cost to break it up into pieces of size delta? Right, and the proof is the same. Proof, change your variables. Right, so the picture is here's my paraboloid, and then I know how to let's say how much does it cost to break up this medium-sized region corresponding to let's see, how should I draw this with enough shading corresponding to this region. If I know how to break up the red paraboloid into pieces of size delta, how much does it cost to break up the green paraboloid into pieces of size delta? Well, you just stretch the green piece to be the whole red piece and apply your change variables, just like in the parabola case. Okay, so this plays just like how this played a big role in the parabola decoupling theorem. This plays an equally big role in the paraboloid decoupling theorem. But we won't state it today because that's a tool we've seen and it's used exactly the same way. Okay, so the remaining features. Okay, so remaining features that are new or at least different. You'll see glimpses of things that we did see in the parabola proof. So the way Borgan does it is that they have one trilinear decoupling constant. So they have trilinear reduction. This uses the broad-narrow analysis due to Borgan and Guth. So this particular paper that came out in the early 2010s, Borgan and Guth gave a new, quite short proof. I mean, so originally restriction was known up to 10 thirds. This was due to bilinear restriction for paraboloids by Terry. And then Borgan gave like a 3-page proof of that, using what was then called, very commonly called, the Borgan-Guth argument. Now it's more commonly called the broad-narrow argument. So I'll show that. And then the key estimate follows from ball inflation, this lemma called the ball inflation lemma. This is the key geometric estimate. And it follows from a trilinear K estimate for tubes due to the proof of these estimates. This first showed up in Bennett Carberry Tau, but then there's a short proof due to Larry Guth. And then, of course, then the last piece will be the iteration. Okay. Of course, we're going to skip the iteration because, I mean, once you have all the estimates, it's a matter of just computing everything. And hopefully by the end of at least the first half of the lecture, we'll finish the trilinear reduction, and then the second half of the lecture we'll be talking about this key ball inflation estimate. Roughly, the way you should think about it is that so I spent a lot of time going up from, when we did the parabola decoupling theorem, going from BB to 2BB, and that relied on some Pokea type estimate. The style of that proof will be similar, although this version will be much more complicated. And this trilinear reduction, in the parabola case, there was a bilinear decoupling constant. Bilinear constants are easy to work with because you can just use Holder to reduce to them. Trilinear decoupling constant, we'll need to do something a bit more clever, and this will involve the uncertainty principle. Okay, and so even though so we're going to concentrate on 1 and 2, and even though it's going to take up the rest of the lecture and possibly more, we're still only going to provide just a sketch. Okay. Great. So let's talk about trilinear decoupling. What is it? And so what is trilinear decoupling? And then why does d of delta reduce to studying the trilinear decoupling? Okay. So here we also once again will have an intermediate parameter. So we're gonna let nu be very large compared to delta, but very small compared to 1. In the end, in the iteration, once again, nu is going to be about delta to the epsilon. Okay, so our trilinear decoupling constant will depend on nu, and so technically I should be writing m of delta comma nu, but since at the end of the proof we're going to choose nu to be some function of delta and epsilon, I'm going to drop that in there. Okay. Okay, so remember in the parabola decoupling case, we assumed that our intervals were separated so that there was what's called some sort of transversality. Now we need the analog of that criteria in sort of 3 dimensions. So, so transversality so sort of like our estimates were good if sort of our sort of intervals were as far apart as possible. So we need some sort of analog that in 3 space. So we say, so given alpha 1, alpha 2, alpha 3 inside -1 squared of side length nu. So sometimes if I'm lazy, I'll call these nu caps. Okay. So given these things, we say alpha the triple are nu squared transverse if the parallel pipe head parallel pipe head spanned by n alpha 1, n alpha 2, n alpha 3 has volume, basically a constant times nu squared. So in other words, let's draw a picture. Here's my paraboloid. Okay, it has some, goes above 0, 1. And then we have 3 little caps down here. Let's say here, and then here, and here. Okay, and then they lift to, let's use another color. They lift to this piece, and this piece, corresponding to these normal vectors. Okay, you can see that that generates a parallel pipette. If that volume has length at least nu squared, then we say that these caps are transverse. So just an example, just what kind of things do you take? Okay, so an example. So let alpha 1 be the ball centered at the origin of side length nu, alpha 2 be the ball centered at the point nu comma 0 of size nu, and then alpha 3 be the ball centered at 0 comma nu size nu. Okay, so this corresponds to taking this cap and some cap right here, and then some cap right here. Okay, and then these are you can compute these caps are sort of nu squared transverse. Basically, you just compute the normal vectors attached to the piece of paraboloid that lives above these 3 caps, and then you'll see that the volume is something like 4 nu squared or something. Okay, so this is sort of the 3-dimensional analog of having my intervals be separated, right? We had to have on the parabola, we needed to have some sort of like nu separation. So this is the higher dimensional. Okay, so now how do we define our decoupling constant? So so definition. Okay, so we're gonna let m delta, which secretly I should be writing m delta nu, but since I'm never going to do the iteration, and I'll tell you ahead of time nu is delta the epsilon, let's just ignore the nu dependence. Okay, so let m delta be the best constant such that, okay, the geometric mean, so I'll define this in a little bit, of f alpha I, L4, let me write down the at first, and I'll say is less than m delta times the geometric mean of q breaking up in alpha i's of fq. Okay, so for all f Fourier supported inside the piece of parabola above the unit ball, and for all alpha 1, alpha 2, alpha 3, which are nu squared transverse nu caps. Okay, so and what's geometric mean here? How is this defined? This is just, so the geometric mean of xi is just x1 to the 1/3, x2 to the 1/3, x3 to the 1/3. Okay, so a lot of people will write, just straight up product, but I like writing geometric mean here, mostly because the LP norm and geometric mean, the LP norm or geometric mean is the geometric norm of the LP norms. That's Holder. So it's a bit cleaner to write out. It's also easy to remember that if I delete the geometric means, okay, this is like saying I know how to decouple each alpha I into caps of size delta, right? But the idea is that with this transversality over here, maybe decoupling them simultaneously will be slightly more efficient than decoupling this d of delta. So yeah, so as you see, unlike in the in the efficient congruencing style proofs, okay, the Borgan-Demeter style proofs sort of weight each alpha I cap, each new cap sort of equally. Okay. Rather than having a 2 plus 4, they want to weight these things as 3 plus 3. So in this case, 4/3, 4/3, 4/3. Okay. Okay, so that's the trilinear decoupling constant. And of course, the moral should be that d of delta should be basically the same as m of delta. Okay. So of course, if I knew that d of delta was small, then I could literally pretend the geometric means weren't there. Then I would know that the m of delta is small. But of course, the idea is that I want to use the m of delta to control the d of delta. So I need some estimate. So I need some estimate like d of delta is bounded by stuff with m of delta. So remember the parabola case, we had that like d of delta is bounded by d of delta over nu plus sort of m at, m, let's say m11 of delta or something like that, right? So we need, once again, some sort of estimate where d of delta is controlled by a nicer term or nicer terms plus the bilinear expression. So here we'll need to basically control d of delta is bounded by d at a certain larger scale plus some sort of trilinear decoupling constant. Okay. Great. Are there any questions? Okay. So, let's see. How should we do this? Okay. So how do we prove some estimate of this form? How do we prove some estimate of this form? Well, what do we want? So we want to show that, the integral of f to the L4 is bounded by something, and this something contains m of delta times by some q and p delta fq, right? Because if we could show this estimate, well, if we can show this estimate with this box, then, because then this would say d of delta is the best constant that I can put here, d of delta is less than box. Maybe d of delta to the 4th. Right? And so that's what we want to show. Okay. And so I'm just trying to say which left-hand side should we start with. And so it suffices to show that for each box of size delta to the -2, then this integral we have this estimate. Let's put 4 here, forward. Right? Because if we have this estimate, then what we do is, well, how do you get this estimate out of it? Well, you just sum over all possible boxes of size delta -2 inside R2 or R3. Okay, you sum over a partition of R3 into boxes of this dimension. And so this sum, of course, is okay, because this goes here. And then if I sum this guy over balls of radius delta to the -2, then I can Minkowski and interchange this, move the sum inside over here. Okay, so it suffices to consider sort of this spatially localized estimate. Okay. Okay, so we need to start with this guy. So what we're going to do, we're going to make use of the uncertainty in a kind of weird way. Okay, so what we're going to do is we're going to say, okay, well, this guy, we're actually going to, so this is a rather large box in R3. Okay. We're actually going to work with slightly smaller boxes of size nu inverse. So we're just going to partition this into boxes of size nu inverse and integrate over balls of radius nu inverse. And it'll be obvious in a little bit why we do this. And furthermore, we're not going to work with F. We're going to work F. We can rewrite as we're going to partition F into balls of radius nu, like so. Okay. So yeah. So remember here, this is alpha is a nu by nu square inside -1 to 1, 2. And here, this is a nu to the inverse by nu to the inverse by nu to the inverse box in R3. Okay. Great. So let's analyze this integral over here. Okay, so we're going to only care about this guy. Okay. Okay, so we study fix. We study this guy. Okay. In particular, we're going to do something that is a bit strange, and we're just going to study this pointwise first, and then we're going to. Okay, so we're going to recall the uncertainty principle. So recall. Okay. The uncertainty principle says that if the length of alpha, if alpha is a square of side length nu, then f alpha is essentially constant on any cube of side length nu inverse, right? So here, remember what the uncertainty principle says. So let's draw a box. Here's my alpha. It's a nu by nu squared. It gets lifted onto the paraboloid. Let's say it's this cap. Okay, this is a, so pictorially, this is a cap that looks like this. Nu by nu squared. And so then f alpha hat lives here. And so that means absolute f alpha is constant on the dual tube, which is nu inverse by nu inverse by nu to the -2. And so therefore, you can pick any cube of side length nu inverse, and you can find a translate of this guy and fit it inside. So f alpha, absolute f alpha is constant on this guy, so therefore it's constant on any cube of side length nu inverse. Right? Are there any questions about this? Okay. So in particular, this is my cube of side length nu inverse. And so absolute f alpha is constant on it. We can pretend that it's independent of x. All right, so we're going to fix. Okay, so let's copy this. Okay, so we fix our ball of radius nu inverse and study this guy. Okay, note that by the uncertainty principle, f alpha of x is a constant that only depends on b nu inverse and not a particular x in b nu inverse. So this is the value of this only depends on b nu inverse and not just particular, is it is it which particular point in B new inverse. It's the same value for all the points in B new inverse. So instead of writing f alpha of x, I'm just going to write f alpha, where implicitly every f alpha will depend on the particular B new inverse that we have. Okay, so now what we're going to do is we're just going to basically sort these. We're going to sort the alphas that give a significant contribution and basically show that there are only 3 scenarios that can occur. Okay, so okay, let's give more space. Okay, so we're going to let S big will be the set of new caps that sort of give a big contribution to this sum over here. If one reads Larry's papers, this is a key sort of tool, I think, a key idea that shows up in his, most of his in a lot of his arguments. So we're gonna let S big be all the points, all the new caps, such that F alpha prime is big. So these give significant. These are the caps, the new caps that give significant contribution to this sum. And by significant, I'm just gonna say that. And it'll be clear why I chose new squared here at the end of the proof. Okay, so you can compare these constants because on B new inverse, these don't depend on x. Okay, so S big here will depend on B new inverse. Note, S big depends on B new inverse. Okay, so 3 scenarios can occur. Okay, 3 scenarios can occur. So you can do this analysis in the parabola case, what I'm about to do, but basically what this almost says is that it just says that either I'm a neighbor or I'm sufficiently far apart. Now, in 3 dimensions, I have 2 directions to go, so there's actually a bit more cases. To summarize what's going to happen ahead, either I am sort of concentrated in one big area, or I lie along a lower dimensional piece, in other words, a parabola, or I sort of am completely transverse. That's the 3 scenarios that are up ahead.
Very quick question. So you already mentioned they are going to use the broad narrow analysis. So this analysis is already start. I mean, can you point out what is the broad and narrow analysis in this argument?
Yeah. So I haven't said it yet.
Okay.
The narrow piece will be when all the significant contributions concentrate along a lower dimensional curve, let's say, or they all concentrate on a smaller piece. And then when they're broad, that's usually the transverse term. Yeah.
Okay, thank you.
Yeah. Okay, so there are 3 scenarios. So scenario 1 is that S big does not contain any 2 squares of side length nu, any 2 alphas that are separated by bigger than 10 nu. Okay, so in other words, so in S, so there's one possibility that could happen. In S big, no 2 alphas are more than 10 nu apart from each other. Okay, what does that mean? That means all the squares in S big are within 10 nu of each other. Okay, so all nu squares, or in other words, all alphas in S big are within 10 nu of each other. Well, I mean, each alpha is a new square, and if all the squares are within 10 nu of each other, that means S big has a bounded number of squares. So S big, the number of terms in S big is bounded in this case. So why is this useful? Why is this useful? So remember, our goal is to control this expression over here, right? Why is this useful? Well, let's look at this guy. So this is alpha in P nu of F alpha. Okay, so I'm either in S big or I'm not. So if I'm either in S big or I'm not in S big. Okay. And okay, so that's triangle inequality 1. I want to do a second triangle inequality. And just move this inside. And okay, so there are a bounded number of terms here. There are only a bounded number of terms, and so what I'm gonna do here is I'm gonna say, well, this guy, this is less than bounded number, so let's put less than tilde times the maximum. And then what do I do here? Well, here I'm just gonna do the union bound. Here, how many terms are not in S big? Well, I don't know, but I know that there's an upper bound on the number of terms, of a number of nu caps inside the unit square. Well, there's nu to the -2 of them. So there's nu to the -2 many terms here. And then since I'm not in S big, how big is each term? If I'm not in S big, then this inequality is reversed, right? If I'm not in S big, then each term is pretty small compared to its maximum. Each term is at most nu squared times the maximum of each guy. Okay? And so then this is just max FL. Okay? So if S big, if the terms that are dominant aren't very separated, then the whole sum is just controlled by the maximum. Okay? That's case 1. How about the second case? So the second case is, of course, this does not happen. In other words, S big contains two sort of big contributions that are pretty far separated. Okay, so this case 1 here says that all the contributions to this sum are sort of concentrated inside one place. Okay, but what if they're not concentrated? If they're far apart, then we have to consider some other things. Okay, so let's copy this. Actually, maybe I should change the template so we don't have to copy so often. Tabloid. So okay, so that's case 1. Okay, so now what about the second case? Okay, so the second case is not, right? So negation of 1. Negation of 1. So in other words, S big, so these are the significant contributions, right? The significant nu caps. So S big contains two alphas that are bigger than 10 nu separated. Okay, so in other words, the picture. So let's look at just this is in minus this is in -1 to 1. Okay, so let's say there are two. So these are all in S big. Let's call them alpha 1 and alpha 2. And then they're at least 10 nu separate. S big contains two alphas that are at least 10 nu. So these red boxes are where the significant contribution to this sum occur. Okay. Now, we're going to let L be the line connecting these two centers. Okay. And we're going to let SL be the set of points inside this unit square such that the distance between these points and L is less than 1,000 nu. Okay? I guess I drew this picture slightly too big. Let's draw it smaller. So we have these small boxes. Okay? These are separated by at least 10 nu. And then we have a giant SL. This is not big enough. Okay. We have a giant SL. Let's slightly make it bigger. So this is SL. And then this length is at least 1,000 nu across. Okay. And strictly speaking, I should only restrict myself to this region. Okay. Okay. Okay, so we have this green strip, this strip that we've now defined. Okay. Okay, so now in this situation, two things can happen. A, there exists a third cap. This is alpha 1. This is alpha 2. There exists a third cap inside S big, but alpha 3 is not in SL. Okay. So either a significant contribution can live outside the green strip, or it can live inside the green strip. Okay. What happens if I live outside the green strip? In other words, this situation. Now we're in this situation. So here are my significant caps. Here's the strip. And then here we have another third significant cap. Alpha 1, alpha 2, alpha 3. Well, okay, so these are distance 10 nu. This strip is of thickness 1,000 nu. So that means these distances, are potential are quite large. At least, let's say at least some constant nu. Okay. So in this scenario, alpha 1, alpha 2, alpha 3 turns out to be nu squared transverse. And what does being nu squared transverse say about our sum? See, not only are they transverse, but they're also in S big. They're significant contribution to the sum. Okay, so that makes life easy. Well, let's see what happens. Okay, so we know that we have 3 significant transverse contributions to this sum. So actually what we're going to do is we're going to be pretty lazy and just say, okay, well, this is bounded by nu to the minus bounded power. Nu to the minus 2 will work of F alpha. Okay. And then each of these terms, I'm going to basically write this as, okay, let's write down the estimate first and then say why. So this will be less than F alpha 1, the 1/3, F alpha 2, the 1/3, F alpha 3, the 1/3, because since I'm in S big, each alpha 3 inside S big, so this implies that if this implies that F alpha 3, let's say, is at least nu squared times the maximum. Right? In other words, the maximum is less than nu to the minus 2 times nu to the minus 2 times F alpha I. Right? Since alpha I is an S big. Okay? So if there's a third significant contribution outside the strip, then this sum here will be controlled by sort of the product of these 3 transverse terms. And you can sort of see that this will be the term that gives the bilinear reduction. if it's trilinear reduction. Okay. Otherwise, no term. Okay, no contribution. There is no significant cap outside the strip. In other words, all the significant contributions comes from this strip. Okay, so in other words, the other situation is that all alpha squares, or all alpha new caps, all alphas, say all alphas outside SL are not in S big. Okay? Or in other words, the maximum over all the caps not in SL, they're not in S big, which means then that all the contributions are less than nu squared times the maximum. They all contribute very small. Or in other words, the maximum is less than nu squared times the maximum of all the caps. So what does this scenario say about this sum? This scenario says, well, okay, so I'm either inside the strip or I'm not. Okay. I'm being slightly lazy in that you can have something that overlap a strip very slightly, but you can always redefine your SL so that it's not quite a strip, but it like is pixelated. But let's ignore that point. Okay, and then if I'm in the strip, then I don't do anything. Okay, that's where the significant contribution is. But if I'm not in the strip, then the F alphas aren't very big. And so how many terms are in this? Well, I don't know how many, but there's at most nu to the minus 2 many. And then each term contributes nu squared times the maximum. Okay. So then once again, I get that I'm either in the strip or I'm the maximum. Okay. So there are 3 contributions. Okay. It's almost readable on the screen here. The first contribution is that this sum is bounded by the maximum. That's when if all the significant contributions of this sum is concentrated in one place. Or the significant contribution could be all controlled by sort of 3 transverse terms. Or the significant contribution can be concentrated inside a lower dimensional piece, sort of along a strip, plus potentially it could be concentrated at some point. Okay, so just to summarize what we've done, we've said that thus. So I also want to point out that of course this all this analysis here depends on S big, right? It depends on the fact that we're working on this Baller radius nu inverse, and therefore F alpha is constant. It's a constant. That only depends on this ball. That's why we can compare these things. Okay? So for all the maximums that I've written, and the choice of L depend on this Baller radius nu inverse. So what have we shown? Let's go to a new page. Thus, for each Baller radius nu inverse, we showed there exists a line L such that the contributions to this guy are either controlled by one dominant piece or one dominant strip. And this is a 1,000 nu neighborhood of L, or some transverse piece. Say, let's even put a maximum, which is harmless. Alpha I R nu squared transverse nu caps. Let's say geometric mean. Okay. So pictorially, if you want to draw a picture to remember what happens, either the contribution comes from a sort of dominant subcap, or it comes from, that corresponds to this term, or they corresponds to some dominant strip, or they come from sort of three pieces, but these three pieces are sort of quite sort of separated. So those are the three scenarios. And I mean, heuristically, this already makes the problem easier because if you can imagine that I'm going to draw a paraboloid that lives above here, and this will correspond to a smaller cap. This corresponds to some sub-manifold of the paraboloid. I've made the problem easier somehow, right? Like I've shrunk the dimension, or I can rescale the problem. And then here I've sort of made my problem transverse. And the moral is transverse problems, there's potential more cancellation. Okay. So okay, great. So now we know pointwise what this expression is. But now remember, what is our goal here? Our goal is to, of course, we just integrate over this pointwise expression. Then we still have to sum over all these balls. Okay. So we need to, well, we first have to raise everything to the 4 power. That's fine. Let's raise everything to the 4 power. Okay. And then we need to integrate. So let's integrate. Okay, so this is B new inverse max f alpha to the 4 plus integral sum alpha L plus integral B new inverse. Here's some new to the bounded power. Max alpha I. Let's just abbreviate it as alpha I transverse times the geometric mean. Okay. And then the last thing we need to do is, of course, we need to sum. Now, the problem is that these maximums depend on B inverse. Okay, so what we're going to do first is then, well, this guy, let's handle this term first. Well, this guy is going to be less than some alpha, some B new inverse f alpha to the 4. And this term over here will be less than, of course, nu to the minus bounded. Let's even do something even worse, alpha I transverse. And then we integrate over the geometric mean. Okay. And then here, what we're going to use is here we will use L2, L4 parabola decoupling. The reason is because, well, I lie on a lower dimensional piece. Okay, so what is the so I know it's already 11, but I'm going to go slightly over time, and then I'll break when I finish this point. So I know I live on the lower dimensional manifold over here. So let's imagine. So how do we analyze this guy? How to analyze? So I won't do all the details, but here's where the sketch of the proof comes in. How to analyze? So let's assume the line L was on the x-axis. Okay, so the bird's eye view is that, well, it looks like this, right? So I have some sort of, this is SL from above, looking from above. SL is this thickness 1,000 new piece. Okay, and then the 3D view is, here's my paraboloid, and then I'm looking at sort of this sort of thin neighborhood of the paraboloid, a slice. And then if I take this paraboloid and I get a knife and slice it downwards, I get a side view. side view. What does the side view look like? So I'm projecting this this neighborhood of this paraboloid onto the vertical axis. I get a side view that looks like this. And this is going to be roughly of thickness 1,000 nu. Okay. And so if I have 1,000 nu neighborhood or let's say I have a new neighborhood. Let's even ignore the 1,000. It doesn't really matter at this level. If I have a new neighborhood of a parabola, how much can I break up? So this is let's say, okay, this is not that great. -1 to 1, -1 to 1. Delete this. -1 to 1. How if what does the parabola decoupling dictate? If I have a new neighborhood, how small can I break these intervals up into? Well, parabola decoupling dictates that I can break them up into intervals of size nu to the 1/2. Okay. So it turns out, okay, that you can use regular parabola decoupling. So it's because all this piece here is concentrated on our lower dimensional piece, concentrated on a parabola. And so it turns out that this expression over here, since it's concentrated on a parabola that's on the paraboloid, this guy is then controlled by the parabola decoupling constant at L4, evaluated at square root nu, times by the sum over all the betas size nu to the 1/2, beta intersect SL non-empty, F beta. Of course, this takes argument that I'm just going to skip, but hopefully I've pointed out. So what happens pictorially is that you end up breaking up this strip SL into little boxes of size nu to the 1/2 by nu to the 1/2. And this turns out because I'm on a lower dimensional manifold, so now I can use parabola decoupling constant. Now, what's the L2, L4 parabola decoupling constant? Well, this is of size 1. So this guy is of size 1. Okay, so then what's now happened? So I have the integral over ball radius nu inverse is bounded by this guy, plus this guy, which is controlled by parabola decoupling, plus this transverse term. So, okay, so what happens now? So now what I'm going to do, I'm going to integrate ball radius 2. Of course, this is just some ball nu inverse, ball delta minus 2, ball nu inverse, f to the 4. I know each of these terms, how big that is. Well, let's do it. So if I sum over the ball and nu inverse over here, well, this sum and this integral just combine. So so what do I get? Then this is then just sum alpha, ball raised delta to the minus 2 f to the 4. Okay. Now what if I sum ball nu inverse here? Well, that means I'm summing ball nu inverse here. And so that this I can turn out to push into here by Minkowski. And so then I get another contribution of a ball a partition decoupling into scale square root nu. I should put a 4 here. 4. And then if I sum ball radius nu inverse here, well, I can union bound and take off further powers of nu inverse. So then I can move into here. And so then after enough union bounds, you're going to get this plus nu to the minus bounded. Nu is delta to the minus that. Nu is delta to the epsilon anyway, so it doesn't matter. And then let's even take another maximum alpha I transverse times by integral ball raised delta to the minus 2 geometric mean f alpha I to the 4. So what's happened now? This guy, I'm going to attack using parabolic rescaling because the problem has reduced to a smaller problem. This guy I'm also going to attack using parabolic rescaling because I've made the scale smaller for free. And then this guy over here is the transverse term. Okay, so this is, and of course you would get, there's a few more details to fill in, but this is roughly how you would reduce studying d of delta into m of delta, because this term I rescale, this term I rescale for free, and so therefore it suffices to study this last multilinear term over here. So that ends the first half. So I've reduced studying regular decoupling to multilinear decoupling. So let's take a maybe 5-minute break, and then when we come back, we're going to talk about how do you actually study this multilinear decoupling concept. So yeah.
Okay, thank you very much.
Yeah.
So 5 minutes break. Thank you.
Yeah. Okay.
Hi, Zen.
Hi.
Would you mind if I ask questions?
Yeah, sure.
Yeah. So so I think this argument works because we know some. So for example, we have to know the R2 parabola decoupling, and we have to know that trilinear Kaka estimate is sharp. Is that right?
No, we don't actually have to know at this point that the trilinear Kaka estimate is sharp. But yeah, you do need to know parabola decoupling, and this is how. So one key input for all the decoupling theorems is that there's a lower dimensional input.
Yeah.
So in the moment, so for example, you could see this in the parabola argument too already. The parabola argument, one key estimate that I needed to use, even in the argument that I presented, was Plancherel, which is decoupling for the line.
Mm-hmm.
Now, decoupling for the paraboloid in R3 will rely on decoupling for the parabola. And decoupling for the paraboloid in R4 relies on decoupling for the paraboloid in R3 for basically the same reason that you sort of, you can't exclude the fact that the significant contributions can lie in a lower dimensional manifold.
Yeah. So eventually, we can use this method to prove for general paraboloid decoupling.
Yeah. But of course, it's very iterative, right?
Yeah,
so
yeah.
quantitatively, it's not very efficient. Yeah.
Yeah,
But there's no like new there. The proof I present is pretty much the only proof of paraboloid decoupling. Is almost, but yeah.
Yeah. So as I mentioned that so we need some estimate for the multilinear Kaka estimate, but we don't need that to be sharp.
No, we do need to. It will turn out we will need to use the sharp trilinear Kaka estimate, but that's not needed in this reduction. It's needed in the proof, but it's not needed in the reduction.
Yeah. I see, but I just wondered since they know they have the sharp Kaka estimate, so they do this reduction.
No, if you there was an earlier version before Borgan and Demeter proved decoupling for the paraboloid. Before Borgan and Demeter was able to prove decoupling for the paraboloid, Borgan himself was just able to use this argument alone and some trivial estimates to prove decoupling in this range. Right. So here n equals 2, this would n equals 3, this would be corresponding to 3, right? It correspond to the square function range. It turned out after a bunch of trial and error that there is this new, and the reason is because the multilinear Kaka estimate they were using is sharp, but it was the wrong one. There's a particular multilinear Kaka estimate that you need to use that you need to. It's not because it's not they have this estimate not because they want to use that multilinear estimate in mind. I mean, this is a natural reduction. I have a linear object I want to reduce to a multilinear object. Once you have this multilinear object, then you need to see sort of what kind of Kakea-like estimate. It's not obvious which Kakea estimate you need to use. It's obvious nowadays because it's been 7 years or 8 years since the paper has come out. But just using broad narrow plus some sort of basic sort of Kakea or trilinear Kakea type estimates, Borgan himself was able to show this particular range. Now, there was an extra ingredient called Ball inflation that I'll talk about very shortly. That was sort of needed to recover this from this range to this range. Okay. They don't do this just because the Kakea estimate is sharp. You do this because this is natural to have. You know, it's sort of now a philosophy. If I have a linear problem, then I should try to multilinearize the problem. This is a problem this is the philosophy even in restriction and Kakea, right? They don't do this because, oh, I have a Kakea estimate in mind. You do this because this is the natural philosophy to do. Whether or not it's, you know, how multilinear do you want, that's up to debate. And then once you reduce to a multilinear problem, then you see what kind of Braskamp-Lee multilinear Kakea type estimates do you have to use to do this.
Yeah. Okay, thank you.
Yeah. All right, great. So let's start. Okay, so now what we did was we reduced to studying. We at least sketched why maybe to study decoupling, we just need to study multilinear decoupling. Okay. So let's recast the question again. So how do we analyze the trilinear object? So let's remember m delta is the best constant such that the geometric mean of these f alpha i's in L4 bounded by m delta times the geometric mean of each of these caps being decoupled into size delta. This should be 1/2. Oops. Okay, and then this should be for all new squares alpha I, which are, okay, new squared transverse. Okay, and then for all f for a supported inside a thin neighborhood of the parabola. A thin neighborhood of the paraboloid above the unit square. Okay, so for this part of the talk, we're sort of I'm going to ignore this. I'm going to pretend that new squared is really not new squared transverse. It's really one transverse. It'll make the geometry slightly easier to talk about. You can do this, and then you can keep this around. And what's going to happen is you're going to lose nu to the minus bounded many powers, and those are delta to the minus epsilon anyways. So for convenience, what we're going to do is we're just going to pretend when I say transverse, I mean one transverse. Or in other words, you know, if I say, oh, you know, some tubes are transverse, you should imagine that these tubes are sort of axis parallel, if you want the maximally easiest example in mind to keep. Yeah, they're not quite, I allow a little, like, you know, I allow nu squared transverse, in other words, they're allowed to have some small angle, slightly smaller angle, but to keep in mind let's not talk so much about, you know, keep track of this transversality parameter. When I say transverse, you should think that they're pretty much like angularly separated as much as possible. They're almost like axis parallel tubes. Okay, it's not so important at this stage. This is only a sketch. Okay. Great. So how do they work with m delta? Okay, so to work with m delta, they consider an auxiliary object. So Borgan and Demeter use the object Okay, and has 4 parameters. One will not. One of them will be fixed. P will be the fixed. P will equal 4. But there's basically 3 parameters. M, P, Q, R, sigma. P is 4. But I don't write 4 here because it's pretty general. This will be the scale corresponding to the spatial. This will be the square corresponding to the frequency scale. And I'll let me write it down first. It's the average over all the balls of radius r inside the ball of delta to the minus 2. You can make this a continuous average if you want. What we're going to do is we're going to make it a discrete average. So you partition ball of radius delta to the minus 2 into balls of radius r, and then you sum over those balls of radius r, and then you average over the number. But you can make it continuous if you want. Times the geometric mean of partitioning the alpha I caps into sigma inverse, and then F theta LQ averaged BR. Okay, so this is a mess, and I'm going to motivate it a little bit. What does this mean? What does this mean? F LQ hash B is defined to be, let's raise it to the q power, it's defined to be the average integral of f to the q. Okay. This is convenient because if f is actually constant on B, then this expression over here is that constant. In the past, people wouldn't do this, and there would be various weird normalizations that you would have to keep track of. But then this terminology started becoming more popular. Some people will write average here. I will write this number sign. Okay, so there's this strange object that has 4 parameters, and only one of them is fixed. P is 4. Okay, so why is this useful? What is this thing? Okay, so why is this useful? Why is this useful? Okay, so let's how much space do I have? Okay, so let's look at MPQ11. Okay, so let's put in the definition. So this is the average over all the 1 balls inside the ball radius delta to the minus 2, geometric mean of all the caps inside alpha I that are of size 1, F theta LQ average over a ball radius 1 squared to the P over 2. Okay, so I just plugged the definition in. And what is the sum here? So alpha I is a new cap. New is, delta to the epsilon. So it's all the thetas that are inside alpha I that are of size 1. Okay, and I want to look at F theta. Well, there's only one of them. Right? So then this guy, there's only one term in this sum. So this is the average over all the 1 balls inside the ball radius 2, geometric mean of F alpha I LQ average over a ball radius 1 times P. Right? Okay, so now we're going to use the uncertainty principle. So F alpha I is constant. So remember, this is a new ball. Length of alpha I equals new. Right? So that means F alpha I is constant on balls of radius nu inverse. And so it's definitely constant on a 1 ball because 1 is less than nu inverse. So definitely constant on a 1 ball. Okay? So this is really a constant on this guy. Okay, great. Let's write that out. So this is 1 over the number of 1 balls inside the ball radius delta to the minus 2, sum over all the 1 balls inside balls radius delta to the minus 2, times by the geometric mean of F alpha I evaluated, let's say, at the center. It doesn't matter. It's just some point inside the ball radius 1 to the P. Right? Here we really use the fact that since this guy is constant on this guy, then this LQ average is exactly what this constant is. This is why the hash notation is convenient. Okay, great. So now let's look at this. Let's look at, okay, so this is 1 over the number of 1 balls inside the ball raised delta minus 2. 1 ball inside ball raised delta minus 2. Now let's integrate over this 1 ball. And then let's say geometric mean f alpha I of x, p dx. This is the same expression, right? Because the ball has radius 1. In fact, we can even put this guy, right? Because the ball has radius 1x. Okay. Are there any questions about this step? So we're very strongly using the uncertainty principle at this point. Okay. And now, well, okay, so now we have a sum of the integral, and the averages multiply. And so then this guy is equal to the average over ball raised delta minus 2, geometric mean of f alpha I to the p. Right? And if we zoom out a little bit, maybe zoom out a lot, this guy is an L4 norm of the geometric mean. MPQ11 is an LP norm of the geometric mean. Right? So this is the left-hand side. This is the left-hand side of M delta. Okay. When I have 1, 1 in these parameters, this is under the uncertainty principle, morally the same as the left-hand side of M delta. Great. Are there any questions? Okay. On the other hand, what is MP, P of delta to the minus 2, delta to the minus 1? Well, let's look at the notation again. This is the average over all the, so now delta to the minus 2 balls in delta to the minus 2. Geometric mean, theta inside P delta of alpha I, F theta, LQ average, or LP average, of B delta to the minus 2 squared to the P over 2. Well, this is the average over all the balls raised delta minus 2 inside the ball raised delta minus 2. That means there's only 1 ball. So this average is vacuous. But then, if you cross that out, well, then this is exactly the right-hand side of M delta. Right? So this is the right-hand side. Okay? So what's the goal here? So if we can show that, let's say, MPQ11 is bounded by something times MPP delta to the minus 2, delta to the minus 1, then, well, this is the decoupling left-hand side. This is the decoupling right-hand side. Then the multilinear decoupling constant is bounded by box. Okay. So that's why they consider this auxiliary object that looks super complicated and has basically 3 or 4 parameters. Okay, so we only need p equals 4. We only need p equals 4 here. So we take p equals 4. And then we study M4Q R sigma. Okay. So there are 3 parameters we get to play with. And there are actually 4 key estimates. 3 of them are sort of somewhat easier. And then there's 1 key geometric estimate. So let me write down the key estimates for the iteration. There's some iterative process. What's going to happen is that you're going to say M delta is bounded by D of delta at a bunch of scales times something. Then it'll look very somewhat similar to the iteration that I presented the parabola case. Well, let's skip all that. Okay, so the key estimates that are needed are so key estimates or key tools for iteration. Okay, we have 1, orthogonality. Let me copy over this definition first. Maybe let's do it like this. Okay, so we have orthogonality. And it says that M for 2, so let's do it this way. If sigma is less than R, then M for 2 of R sigma, is less than M for 2 of RR. Okay. This, I just want to point out the L2 here is from the Q, and so here's an L2. So things with L2, you should probably use Plancherel, and that's indeed the proof. 2, there's a key estimate. And this is the estimate that follows from Trilinear Decoupling, and we're going to talk a lot about it. M for 8/3, right here, where the 8/3 comes from. RR is bounded by R to the epsilon times M for 8/3 R squared R. And then there are a third estimate that just, and the fourth estimate that follow from Holder. So this is Plancherel. These two estimates follow from Holder. And you can see that they'll follow from Holder because I'm going to write them down. MPQ1 of R sigma is less than MPQ2 of R sigma. If Q1 is less than Q2, this is Holder. And then if 1 over Q equals alpha 1 over Q1 plus 1 minus alpha 1 over Q2, then MPQ R sigma is less than MPQ1 R sigma, the alpha 1, MPQ2 R sigma, 1 minus. Okay, so I'll leave these as exercises, and we're going to only talk about the key estimate. Okay, and it turns out that once you patch everything together and apply some trivial bounds, like how is MPQ R sigma related to D of delta, okay, and at various parameters, it turns out you can finish. So what we're going to do is we're going to talk only about the key estimate. Okay, talk about where this 8/3 comes from, and you can almost see that sort of this is, you can sort of already see that in the parabola case, something significant was going from BB to 2BB, right? Squaring the, this is going from nu to the B to and nu to the B to nu to the 2B and nu to the B, right? This is there's something similar happening here. I mean, it's not quite because these parameters aren't both frequency scale. You're squaring the spatial scale while keeping the frequency scale the same. But like, and this is what sort of spurred people to think that, oh, maybe there's some relation between decoupling and efficient congruence. You see these sort of iterative steps that maybe vaguely look familiar. Yeah, but okay. So let's talk about the key estimate. Okay, so what we're going to do is first digress and talk about trilinear Decoupling. And then we're going to come back and prove the key estimate. Okay. So trilinear Decoupling. Okay, so these of course these estimates, n linear Decoupling in Rn. This is proven by Bennett Carberry. We're only going to take the n equals 3 version. So there's a short proof by Larry Guth. It's literally called a short proof of the multilinear Decoupling inequality. It's about, I think, probably like 5 pages or 7 pages, and the proof itself is maybe 3 pages, and it's a nice induction on scales argument. Though the result was first proved by Bennett Carberry. Okay, and we're going to state this estimate in sort of the context of decoupling. So so we're going to let let's say T1, T2, T3 be 3 sort of transverse, and when I say transverse, I mean one transverse. You could say, new transverse, and then your estimates would have some power of new. But let's make life easy, okay? Let's state the most basic form of this estimate that we can think of. Although the way I state it means if everything is purely one transverse, I don't think you lose an r to the epsilon. But let's be a bit not precise, just to get the big picture going. Okay, so let T1, T2, T3 be three sort of one transverse collections of r to the 1/2 by r to the 1/2 by r tubes contained in a ball of radius r. Okay, so you can imagine you have a 3D ball of radius r, and maybe you have a collection of tubes that point this way, and then you have another collection of tubes that point this way, and then you have another collection of tubes that point this way. Okay, and let's say that the angle you take, one from. Maybe I should have changed colors a little bit. Let's do purple. You take one purple, one blue, one red tube, and look at where the normal directions. They create a parallel pipette that has volume. Let's say at least one. Okay, so let's say I'm in this scenario. I have three collections of tubes that look like this. Then the average value of this product to the 1/2 is bounded by r to the epsilon times the product of the average value of this function fj for all fj of the form some constant where the tubes lie in Tj. Okay, so what does this say? So I have three collections of tubes. They're all transverse. Okay, they all sort of, the purple, blue, and red tubes all sort of intersect at well, they all form a parallel pipette of volume, at least one. They're transverse. They're all like axis parallel. Okay, then given any function which is of this form, is just constant times the indicator function of these tubes, the average value to the 1/2 of over this ball radius r is controlled by the sort of product of these averages. Okay? So to explain the 1/2, let's think about why is there a 1/2 here? Right? And sort of what's the 2D analog? Remember in the 2 dimensions, the 2D analog was basically that the ball radius r of f1 times f2 is basically the same as the ball radius fr times f1 times the ball radius r f2. Okay, but I'm in higher dimensions. And the key example was basically just, well, this picture. Okay, so why the 1/2? Why the 1/2 here? So let's explain the why of the 1/2. I'm not going to explain the proof because, well, you can read Larry's very short and nice proof of this estimate. Okay, so let's try to explain, how do you remember the numerology? Why is there a 1/2 here? Well, example, let's talk about the example. Let's talk about the following example. Let's take the ball of radius r to be the ball centered at the origin of radius r. And let's take fj to be, okay, let's take f1 to be the tube, say, how do you draw this? Let's just draw it. I have 3 highlighters. Okay, let's take f1 to be this tube, f2 to be this tube, and f3 to be this tube. Let's draw it. Okay, so this is f1, f2, f3. Okay, great. So at the origin, so this is so these are of size r to the 1/2. This thickness is r to the 1/2. And of course, this is r tall. So this ball over here, this is a r to the 1/2 by r to the 1/2 by r to the 1/2 intersection. Right? So now, what's the left-hand side? Left-hand side is, well, the average of the volume of a ball race r is 1 over r cubed times by the product of these three functions, right? Well, the product of these three functions, the 1/2, is still the indicator function of the intersection. So that's still r to the 3/2. Okay, so that's r to the 3/2. This is r to the minus 3/2. Right? Then the right-hand side, what's the right-hand side? Ignoring the r to the epsilon. Well, the right-hand side is the product of so what's the volume of each of these tubes? Well, the volume of each of these tubes is the volume of each of these tubes is r to the 1/2 times r to the 1/2 times r. So that's r squared. So r squared, but then it's averaged over a ball radius r. So then I divide by 1 over r cubed, and then I take a 1/2 power. So this gives me r to the minus 1 to the 1/2. So that's r to the minus 1/2 times 3 times. So that's r to the minus 3/2. Okay. So this is the right estimate to consider. I mean, at least from the typical example. But of course, I encourage you, if you're interested in this estimate, to read this very nice short proof. But okay, so let's take this as fact. So if a function is just constant times a bundle of sticks, and I have 3 bundles of sticks, and my function is just constant times the bundle of sticks. Okay, if I have this situation, then I have this estimate. Okay, so why does this key estimate boil down to this estimate over here? Okay, so let's now prove this estimate. So how does m for 8/3 RR bounded by m for 8/3 r squared follow from this? Okay, so over here I wrote an r to the epsilon. You can already see that there's going to be an r to the epsilon coming from here. There'll be another source of r to the epsilon, so I'm going to ignore these r to the epsilons and pretend that they don't exist. But if you're more careful, you can keep track of them. So what do we want to show? If you undo the definitions, what do you want to show? Want to show that the average value over all the balls radius r inside a delta to the minus 2 ball, geometric mean, partitioning an alpha cap into r inverse in L8/3 times square to the 4 over 2. And there is a reason why we have 8/3 here. This will be convenient. Is bounded by average ball radius r squared, ball radius delta minus 2, geometric mean theta in r inverse. Okay, so all I did was rewrite the definitions. Okay, great. So what does it suffice to show? So suffice to show for each ball radius r squared inside ball delta minus 2, we have the same estimate except we can erase this average, and we erase this guy, ball radius r squared. because once we have this estimate, what we do is we just average over this guy, average both sides, and then we get this estimate over here. Okay, this suffices to prove this estimate. We're just making our life easier for now. Okay? We haven't done anything significant. Okay, so why is so first of all, this lemma is called the ball inflation lemma. So in the Borgan and Demeter study guide for decoupling, this result is called ball inflation. Why is it called ball inflation? Well, we notice on both sides it's basically the same expression, except for one difference. This spatial ball of radius r over here, this spatial ball of radius r has been increased to a ball of radius r squared after applying this act. So this is why it's called ball inflation. I've inflated the ball from ball of radius r to ball of radius r squared. Okay? So if you see in the literature in Paraboloid decoupling, or in the Borgan-Demeter-Guth moment curve decoupling theorem, there's a lemma called the ball inflation lemma, and this is where the terminology comes from. I inflate this ball of radius r to ball of radius r squared. Okay, so let's at this point we could proceed with the proof, and then we could apply trilinear decay, and then what we'd realize is that there's a particular reverse holder that we would like to be true. So what we're going to do is, to avoid doing that, we're going to turn on the following cheat. It's mostly just technical. So cheat. Okay. So for each I, pretend that the non-zero contributions, the non-zero, let's see, pretend the theta inside P alpha I, which correspond to non-zero f theta L8/3 number BR squared, all are valued, all have value about the same, and let Ni be the number of non-zero contributions. Okay, so the sentence is basically saying, for each I, assume that the value of the so either this for each theta inside this cap, okay, assume that either this guy is 0, or if it's not 0, assume that there's some sort of uniformity. Assume that they're all about lambda I. Okay, and we're going to call Ni the number of non-zero sort of terms in this sum. And you can do this by dyadic pigeonholing. And what you should actually do is you would create these sets theta I, lambda I. These are all the theta inside P R inverse alpha I, such that the value of this guy is at least lambda I over 2 and less than lambda I. Okay, and then there's some logs that you would lose. Okay, but let's pretend for now that the number of terms in this sum that are non-zero is Ni, and if it's non-zero, the values of these terms are the same. Okay, that they're all about lambda I. And you can get there after some pigeonholing. You can assume this uniformity after some pigeonholing. So what do we want to assume? What do we want to show? So we want to show that the average over all the balls radius r inside a ball radius r squared, the geometric mean of partitioning my new caps into R inverse caps, side L8/3 average ball radius R squared to 4/2 is less than geometric mean of the, so how many terms are there here? Well, there's ni terms to the 2. So ni terms squared. And each of these terms, if it's non-zero, contributes a lambda I. And so lambda I squared to the square. So that's lambda I to the 4. Okay, so this is what we want to show. Okay. Great, so we've done pretty much nothing at the moment. We've just sort of tried to reduce the problem, but we still haven't seen where is this Kakea typing point. Right, and now we're going to start using the Kakea typing point. Okay, so so that's what we want to show. Oh, great, I still have some room. Great, so theta is a cap of size R inverse. So that means f theta is constant on BR, right? Just by the uncertainty principle. F theta is constant on BR because these scales are inverses of each other. The average value, the 8/3 doesn't matter here. The average value of F theta over the BR is basically the same as just F theta evaluated, let's say, at the center. Okay. So what's the left-hand side? So the left-hand side of this object is, okay, so this is the average Baller radius r inside baller radius r squared times the geometric mean of the thetas inside PR inverse alpha I. And then this is just the value of f theta evaluated at the center squared to the 4/2. Okay, so what is this? Well, this is the average, the number of BR and BR squared times the sum BR and BR squared. Now let's do, let's also put another average integral over here times the geometric mean, the sum times f theta x squared to the 4/2 dx, right? Because f theta is constant on BR. So that means the value of this function, this whole thing is constant on a Baller radius r, and the average just means I ignore the value. So this is the average value of this function on BR, and the average value of this function is actually the value. So this is equality under the uncertainty principle. And so then I can sum up the average again. So this is average over Baller radius r, geometric mean, sum this guy. Okay. Great. So now I'm getting to I mean, you can, okay, so what do we want to use? We want to use this sort of Kakea type thing, right? I need to see a 1/2 power. I need to see a product. Okay. And you almost sort of see it, right? The geometric mean gives a product. There's no 1/2 power yet, and I have no idea where 8/3, where does 8/3 come into play? Okay, so now we're going to do the following. Okay. So let's copy this guy. Okay. And now, what we're going to do is we're going to actually apply holder. Oops. Holder. Apply holder. Geometric mean times sum. Okay. And the reason why we apply holder is so that we can take advantage of Kakea in a little bit. The particular holder we're going to do is this one. 3/8 times 4 times by number of terms is 4 times 1/2 minus 3/8. Okay, the way to remember it is ignore the 4 here, ignore the 4 here, and then L2 bounded by 8/3 and then N 1/2 minus 3/8. Okay, so now, well, what is this equal to? Well, let's write out the geometric mean now. the geometric mean, so this is average integral, product I from 1 to 3, sum theta in PR inverse alpha I, f theta to the 8/3, and then this is a geometric mean, so the 1/3 power takes out the 3 here, and 4/8 is 2. So this is why we had an 8/3. This is a 1/2, right? And then times, let's move the whole geometric mean out. So this is the geometric mean of these ni's. The 4 times 1/2 minus 3/8, that's 4 times 1/8, so that's 1/2. Okay, great. So this is something we would want to use the multilinear Kakea estimate on, right? And so, right, so what we're going to do, now we're going to apply trilinear Kakea to fi equaling sum theta in PR inverse alpha I, f theta 8/3. Now there's one thing to check, that like the fi's are a bundle of sticks, and f1, f2, f3 are 3 bundles of sticks that are sort of transverse to each other. But that's indeed the case, right? So so in the Ball radius r squared, okay, f theta is equal to, by the uncertainty principle, all the tubes that are r by r squared, pointing in the normal direction corresponding to theta, times ct times it. So if I raise everything to the 8/3, I can do this. And so the picture is that, well, okay, so here's my alpha 1. And then inside each alpha 1, there are some thetas. Okay, and they have very slightly different normal directions. And to each theta, I have a bundle of sticks pointing in this direction, in basically the same direction. And so then, the sum of all the theta is equal, of course, to the sum of all the thetas times all the sums over all the tubes pointing in the normal direction of theta, times ct 8/3 1t. And so I have this bundle of sticks that sort of, broadly speaking, point in this direction, right? And then alpha 2 over here has a bundle of sticks that basically all point in this direction. And alpha 3, the alpha 3 is here, have a bundle of sticks that basically all point in this direction. Right? And these are all transverse because alpha 1, alpha 2, alpha 3 are transverse caps. So I can apply trilinear Kakea to this function. Okay. What happens if I apply trilinear Kakea to this function? I get, so apply trilinear Kakea to get, okay, what does trilinear Kakea say? Well, trilinear Kakea says that this is less than, so I can take the product out, and then I put the average in over the function. I raise it to the 1/2. Of course, here I still have the geometric mean of ni to the 1/2 over here. Okay. Great. And so what is this guy? Well, this is then the product I from 1 to 3 of, so I interchange the sum and the integral, sum theta in PR inverse alpha I, f theta, L 8/3 averaged, Ball radius r squared, the 8/3 to the 1/2 times the geometric mean of ni to the 1/2. Now we assume our uniformity. So Okay, so now we need to assume we have some. So remember, we assumed that there were ni terms that were non-zero, and when I'm non-zero, I'm basically lambda I. Okay, so this is then the product I from 1 to 3, ni lambda I, the 8/3, the 1/2 geometric mean, ni to the 1/2. And so if you look at this, this is geometric mean, ni to the 3/2, lambda I to the 4. Yeah. And then this is geometric mean times ni to the 1/2, which turns out to be the geometric mean of ni squared lambda I to the 4. And that's exactly what we want. And so yeah, that finishes the proof of this key estimate over here, and shows how this estimate sort of follows from trilinear cacao. And yeah, so the 8/3 was basically because so that you could use this holder step over here so that you would result in the correct exponent that you would have. Yeah. And so that's why there's a third parameter. There's a spatial parameter, frequency parameter, and an extra parameter so that you can use your multilinear K estimate for some applications of multilinear. So yeah, so that's all I have for today. This is a sketch of all the key ideas. The higher dimensional proof of the paraboloid is somewhat similar. Your multilinear, you'll have a n-linear decoupling constant that you'll show is equivalent to the linear decoupling constant, basically using the Borgan-Guth argument that I summarized earlier over here, except now there are more lower dimensional. Well, okay, in the paraboloid decoupling theorem, you only use n-1 dimensional paraboloid in this step, and then there's going to be some sort of multilinear Capet input that also comes from Bennett-Covery-Tau or Larry's short proof. And then once you patch everything together, the iteration is fairly quick and shows that you show that decoupling for the paraboloid is true. If anything, more theorems, a lot of this theorem is this proof is sort of the sort of stereotypical proof of decoupling for a lot of things. A lot of sort of broad strokes in how decoupling theorems are proved, in that you first have sort of a multilinear reduction. Once you have a multilinear reduction, you reduce to some sort of Kakea type estimate, and this Kakea type estimate might be quite complicated, so you need to check whether or not this estimate is true. This estimate then, there's this very general sort of Braskamp-Leib type conditions that you can check, and this is a linear algebra condition, and so then the paper is reduced to computing some sort of fancy linear algebra. And so that's how a lot of these papers have been proven. It's somewhat different from the philosophy of Woolley's sort of the nested efficient congruence style proofs, but a lot of the decoupling proofs have this structure. And so hopefully you will have had some glimpse of how decoupling theorems are proved, and yeah, that's all I have for today. Thanks.
Thank you very much. That's really, really great.
Thank you.
So any questions? So I have a question. So all the arguments here essentially work well for any higher dimension?
Yeah. The arguments, nothing in this particular. The only reason why I picked R = 3 was because I could draw all the pictures.
Yeah, okay.
And then you don't have to keep track of all the numerology, right? Like in high dimensions, instead of 4, you have 2 times d plus 1 over d minus 1. Instead of 8/3 over here, where's 8/3? Instead of 8/3 over here, you have, I think, p times n minus 1 over n or something like that. The numerology